Hi everyone, my name is Amitesh, and in this video we're going to do a step-by-step tutorial on how to graph the function y equals x log x. So if you're confused about graphing or just want to brush up, this video is for you. We're just going to master this one by one, considering the derivative, the second derivative, what are the minima, maxima, when the graph is increasing, decreasing, concave up, concave down, etc. Okay, so we're going to do it step by step, and this is as I've taught multiple times at Princeton University in freshman calculus. I frequently graph functions like this, and this is a fundamental example because a lot of cool phenomena comes up, as well as practicing with logs, which can be a bit of a tricky concept in calculus. So let's just dive right into it. Very first step when graphing any function, step one, okay, it's always number one, find the domain of the function, okay? So find the domain. That is number one. We want to find the domain. So what we can do here is we can just think about what the function is. It is x times log x. So the domain is going to be when this function is defined. Now whenever we think about domains, and I've done videos on domains of functions, please check them out. All content's on my channel, links in the description as well. But generally we want to think about square roots, dividing by 0, and taking logs. We can never take the square root of a negative number, we can never divide by 0, and we can never take the log of 0 or a negative number. So those are the things you need to keep an eye out. They are just basically 99.99% of finding the domain problems in calculus. So here we've got the log. We cannot take the log of 0 or the log of a negative number. So the domain is just going to be all positive numbers, which is just going to be the interval 0 infinity. And I've also done a video on interval notation, so check that out as well if you want to brush up on that. This is just meaning all positive numbers. Okay, so that's number one. We've got that down. So when we graph our function, so we can kind of set up our graph already. We have an x-axis and a y-axis. We're just going to be graphing on the right of the y-axis. Okay, so that's number one. Number two is we want to figure out, what's going on with this function at the extremal ends of the domain. What are the x-intercepts? What is the derivative, etc. Okay, so let's start off with the derivative because it's always fun to take the derivative. So what is the derivative of the function? So at this order, it doesn't too much matter what you do. You have to do all of them anyway, but find the derivative. So let's find the derivative. There's no particular order here. I'm just going to find out the derivative. So y prime is going to be, it's the product rule. It's x times log x. So differentiate x, multiply with log x. So it's going to be 1 times log x plus multiply x with the derivative of log x. And the derivative of log x is 1 over x. So it's going to be x times 1 over x. So this is just going to equal to log x plus 1. Okay, so that's going to be y prime. Okay, it's going to be log x plus 1. And now we want to set the derivative equal to 0 to figure out what the critical points are and where the minima and maxima are. Okay, so let me get into that now. So I'm going to now, maybe I will even erase this graph that I've just drawn, just to kind of create some space on the board. So we're now going to figure out when is the derivative equal to 0. So we can set y prime is equal to 0. So y prime is equal to 0. Well, that happens when log x plus 1 is equal to 0, or just when log x is equal to minus 1. Okay? So when is log x equals to minus 1? You can always exponentiate on both sides. When you solve an equation, log is something. Log and exponential are inverses of each other. So that's just going to be the same as saying that x is going to equal to e to the minus 1. Okay, and you can also check. E to the minus 1 is 1 over e. So it's going to be 1 over e. That's going to be the critical point. Okay, so x equals 1 over e is going to be a critical point. So we can write that down. X equals 1 over e is a critical point. Now, the other thing about log is we're just going to sort of look at this quickly. We want to figure out the critical point, which we've done. We also want to figure out where the function is increasing / decreasing, right? So when is the derivative positive / negative? Okay, so that's step 3. Once you've done step 2, okay, so if you're finding the derivative, the next step is to find the critical points and where the function is increasing / decreasing. So what you can do is, that the derivative of y is going to be, we've just seen that y prime is equal to, so I'm just going to use this with black pen. The derivative is log x plus 1. We know that log is a increasing function, right? Because we can sort of graph log. I've done a video on that too. So log kind of goes up, you know, and it's increasing function's derivative is 1 over x. So it's always positive as long as x is positive, which is the domain of log. So you know that the sign chart y prime, it's going to be negative and then positive. It's going to switch at 1 over e. Okay, so y prime is going to be less than 0 on the interval 0, 1 over e. Y prime is equal to 0 at 1 over e. And y prime is going to be greater than 0 on the interval 1 over e, infinity, which is all numbers beyond 1 over e, greater than 1 over e, and all numbers less than 1 over e, it's less than 0. Okay, so therefore what we know is that we can figure out that x log x, so I'm just going to now erase this all off, so we can kind of get our conclusion. X log x is going to be increasing on this interval and decreasing interval 0, 1 over e and decreasing on the other interval. Okay, so x log x is increasing, I guess you could say decreasing on 0, 1 over e. So it's going to be decreasing on 0, 1 over e, decreasing on 0, 1 over e, and it's going to be increasing on 1 over e, 1. 1 over e, infinity, my apologies, 1 over e, infinity. And actually the one I mentioned, because I'm already thinking about the next step, is now we kind of understand something about the graph, right? It's where it's increasing, where it's decreasing. Now the next thing we can do, and this is something I like to do, you know, at the beginning even, before I even find the derivative. I sort of found the derivative because it's fun, but just like to understand what the graph is doing at the ends of its domain. Okay, so these are limit calculations. Okay, so then we can kind of connect the dots. If we know what it does near 0, then what it does near infinity, we can then use the fact that it's decreasing and increasing to kind of connect the dots, and then we just have to adjust the shape to figure out you know, where it's concave up or concave down for the second derivative. Okay, so what we can do is, before we even get to that, let's actually just figure out what 1 over e is briefly, because we've already studied the derivative. So you can actually see that there is a change in sign. You know, y prime is going from negative to positive at 1 over e. Okay, so if you think about it, it's decreasing until 1 over e, then increasing after 1 over e. So is 1 over e a local max or a local min? Pause the video and think about it, and think about, you know, even using the second derivative test as well, just as an extra bonus to understand this. So it is going to be a local min, because it's decreasing and then increasing, right? So the graph is going to go down and then up. Okay, so we can kind of even sort of see that here. So 1 over e is going to be a local min. It's also going to be, is it an absolute min? Is it the absolute smallest the function ever gets? Okay, so it's a min, it's a minimum. In fact, it is also an absolute minimum. So the second derivative test would not have told you that. Okay, so the second derivative test tells you, so we know y prime is going to be log x plus 1. So therefore y double prime is going to be 1 over x, okay, which is always going to be positive on the domain. So therefore y equals x log x is going to be always concave up, right? So y double prime is greater than 0, it's going to be concave up. So what we can do is we can say this is concave up. Okay, and the second derivative test, it does not tell you whether, it tells you it's a min, because we know the double derivative is positive, so it's going to be a min. But because the function has only one critical point, and the derivative changes sign only once, it decreases then increases, that has to be the absolute min, right? It's decreasing until that point, then it increases. So it can never go below that point, right? So that actually has to be an absolute min. So this is a min, in fact, an absolute min. And the second derivative test would not have told you that it's an absolute min, but we know that it's an absolute min just because there's only one critical point. That's kind of where we're getting that. Okay, so we sort of understand what's happening to the function. So now we've got some pretty good ideas about what the function is doing, and I'm going to now erase this, and kind of the last thing we need to do, so we've got some good shape sense of the function, its shape, you know, where it's increasing, decreasing. One other point is x-intercept slash y-intercept, okay? Last point before we kind of move on to the limits, what happens at the endpoints. What are the x-intercepts and y-intercepts? Well, 0 is not in the domain. You can't take log of 0, so there is no y-intercept. For x-intercept, we want to set the equation equal to 0. Okay, so x-intercept is going to be, so this is kind of step 3. Okay, so I'll even write it down. So step 2, Step 3 is finding where it's increasing, decreasing. Then step 4 is finding the second derivative. Then maybe we could sort of say this is step 5, is x-intercept, y-intercept. So for the y-intercept or the x-intercept, we set the derivative equal to 0. So we're going to say that, we set the function equal to 0. So x log x is equal to 0. Well, log x log x is equal to 0. X is never 0 because on the domain x is positive. So therefore, log x is 0, which implies that, you can again solve this by exponentiating, or you get good at sort of what log is, right? Log of 1 is 0, right? So you can also say x is equal to e to the 0, which is equal to 1. Okay, so x equals to 1 is the x-intercept, and now we've got some pretty good idea of what the graph is doing. So I'm going to kind of actually erase this all here and kind of sum up some part of the graph without going into too much detail. So the part of the graph that we kind of have figured out so far, we figured out most of the graph. We just need to figure out what's happening at the ends. So here what we can do is we can sort of just draw the graph. So I'm just going to try to draw the graph here. So it's the x-axis and the y-axis. So we know at 1 we have an x-intercept. We know 1 over e was where the critical point was. Now 1 over e is greater than 1, so 1 over e is less than 1, right? So 1 over e is even less than a half because e is 2.7 something. So 1 over e is going to be somewhere here, right? 1 over e. And we know that what is the value of the function? At 0 we know the value of the function, at 1 is 0. What is the value of the function at 1 over e? Okay, so that's the other thing to figure out with the critical point. Where, when you're graphing, what's the y value? So when x is equal to 1 over e, okay, so I can sort of do this. When x is equal to 1 over e, x log x is equal to 1 over e times log of 1 e inverse. So powers come out in logs, so -1 comes up front, and log of e is 1, so it's going to be -1 over e. Okay, so we're going to get a -1 over e here, and we're going to get this kind of value, and we can sort of connect our graph, right? So we sort of know what our graph is doing, but we don't know what it's doing near 0 and near infinity. That's why I have kind of just drawn a piece of it. Let's just dive into that and finalize the problem. Now you could have done this at the beginning. You need to find limits at the extrema lens, okay? And even for absolute mean and absolute max, you do technically have to do that. This is a special example where there was one critical point that was decreasing and then increasing, so you know that the extrema lens don't have to be tested. Okay, so that's kind of a special case. But now let's find out the limits. So we can work out what happens at the endpoints. So limit x goes to infinity of x log x. Well, what's going to happen? Well, log is going to go to infinity. As I said, I've done a video on graphing logs, so I've explained that. Check it out, okay? It's all on my channel, links in the description. But log of e to the 10 is 10, log of e to the 100 is 100. So it grows slowly, but eventually it gets as large as you like. E to the million, log of e to the million is a million. So this goes to infinity. So with limits, just think about, first thing to get a sense of what's going on is think about what's happening to each piece. So x is going to go to infinity, log x is going to go to infinity. There's nothing to that. Infinity times infinity is always infinity. It's not like 0 times infinity, just picked up the market cap. It's not like 0 times infinity where it's an indeterminate form, it's just going to be infinity. Now the next thing we can do is figure out limit x goes to 0 of x log x. So limit x goes to 0 of x log x, and this is going to be a right-hand limit, okay? So just to be very precise, because we know negative numbers are not in the domain of our function, so the right-hand limit, x goes to 0 of x log x, is, well, what's going to happen here? So again, we think about each piece separately and try to feel for it. So x is going to go to 0, right? X is going to go to 0. Log of x, what's going to happen? Well, log of really small numbers, and it may even help, since I've sort of talked about this so much, just a quick, you can sort of check my video for more details on this, but the graph of log looks something like this. Okay, x-intercept at 1, it kind of looks like that. Log of a very small number, log of e to the negative 1000. E to the negative 1000 is 1 over e to the 1000. It's a very large number on the denominator, so a very small number. But e to the negative 1000, log of that is negative 1000. So log actually goes to negative infinity. So this is an infinity times 0 indeterminate form, okay? So 0 times infinity indeterminate form. And in order to work out this kind of limit, what we're going to have to do is we're going to have to make it a 0 over 0 or an infinity over infinity, and then work out with our standard techniques for those. So I'll sort of talk us through that, because this is going to 0, this is going to negative infinity. They're going at different speeds. Okay, so the product may match with anything, we don't know yet. For example, a limit I always like to think about is limit x goes to 0 of x times 8 over x, right? X is going to 0, 8 over x is going to infinity. Suppose you have a right hand limit, so 8 over x is getting really large. But the product is, because x is non-zero, x is just approaching 0, the limit is just going to be 8. So, it's an indeterminate form. You don't know what it is. I mean, you could have replaced the 8 with a 5 or a 6 and got any other number as a limit. So we really need to understand this. So what we're going to do is, and I'm going to use L'Hopital's rule. Okay, that's going to be the easiest way to study this limit. What we're going to do is we're going to try to do this trick where 1 over something. Okay, so what we mean by that trick is the following. If you haven't seen this trick before, this is a cool trick and it's really worth knowing. X times log x is just going to equal to limit x goes to 0 of log x divided by 1 over x. Okay, so if I divide by 1 over x, it's the same as multiplying by x. But now we notice that the log x goes to negative infinity and the 1 over x goes to infinity. So we get an infinity over infinity indeterminate form, which you can then apply L'Hopital's rule to figure out what that should be. And the other way of doing it was to put the 1 over log x at bottom, but differentiating it would have been harder, because 1 over log x seems a little bit more annoying. So it would actually make it more complicated. So sometimes you have to be clever about, the log x differentiates, the log goes away, right? It becomes, that's why I get L'Hopital's rule, because I know that when I differentiate log, it becomes something 1 over x, something nice. The log disappears for good. We don't really understand it so well. Well, in theory we don't. So we want to kind of make it go away. So by L'Hopital's rule, we can say you check always it's an infinity over infinity indeterminate form. Then you get 1 over x divided by minus 1 over x squared. Okay, so it's a power rule. 1 over x is x inverse. Differentiate, you put the minus 1 and then reduce the power of x inverse by 1. So it's minus x power negative 2, which is 1 over x squared. So you get minus 1 over x squared. Now you can put this up top. So you're going to get limit x goes to 0 of minus x squared over x, which is equal to limit x goes to 0 plus of minus x. And that's just going to be equal to 0. Okay, so that's going to be the answer. And the idea here is that the x term kind of dominates. Even though log x goes to negative infinity, log growth is very slow. Okay, so that's kind of the principle here, intuitively. That's how you intuitively know. Log, as you said, log of e to the million is only a million. E to the million is huge. It's more than the number of atoms in the universe by factors of 10 to the 500 or whatever. So it's a really huge number. So basically we know that because x is kind of, log growth is very slow, log goes to negative infinity also very slowly, so you expect this to be 0. So now you can kind of finish off the graph. You know that you've got at 0, you got a limit of 0, so you put a hole here. It's a hole because it's not defined at 0, right? So you get a hole, and then this kind of keeps going, right? So that's going to be the graph. And it should be concave up. Okay, so I've kind of drawn it. I've not drawn it very perfectly, but I should sort of draw it like that. That's concave up. So that's going to be the graph of x log x. Everything's done there. This is kind of telling us that the limit as x goes to 0 plus of x log x is going to equal to 0. And this is telling us the limit of x goes to infinity of x log x is equal to infinity. So that's going to be the point. And we can sort of say here, plus 1 over e minus 1 over e is an absolute minimum. So it's always good to label, the critical points on the graph. It's an absolute minimum. So thank you so much for watching. This is an important graph. I've done this in lectures at Princeton University and sort of just summarize it in 20 minutes. And it's really helpful to master this. You've got a lot of cool concepts coming in. So, I hope you love this video. Please like and subscribe. It means so much to me you've watched so far. Thank you so much. Time is money, and I hope I've been able to support you with this video. So, and if you just leave a like and subscribe, it takes an extra second, but it keeps you notified of new content, and I'm going to have infinite free accessible math education But also, my goal is to disseminate my videos and help as many people as possible. And by liking and subscribing, you really help me achieve that goal to help people like you, if you benefited from this video, and ultimately create free accessible math education at all levels worldwide. So I wish you all the best wherever you are in the world watching. I hope you do super well, in your math classes and in your life as well. And drop a comment down below. I'd love to hear your comments, and keep up to date with my channel. Check out my other videos, all kinds of cool stuff out there. And I'm super excited to see you in the next video. Thank you so much.